Today we start chapter 7, which is about graphs, and we start with the introduction where we just introduce the main notions about graphs. So here's the definition, 7.1.1, and it says a graph G equals VE consists of the set of vertices V and set of edges E. Each edge from E is associated with two vertices. So here is an example. So here is A, B, C, D, E. And then we have connectors. Here is E1, here is E2, E3, E4, E5, E6. So, set of vertices, that's A, B, C, D, and E. Set of edges is E1, E2, E3, E4, E5, and E6. And then for each of them, it associates certain vertices. For example, E1, we'll say the following: A, E1, B. And then the order doesn't matter, do we say A1B or B1A? Actually, if you think of this as a binary relation, then we can say that we are here considering symmetric relations. And then A, E2E, E, E3D, D, E4B, then A, E5C, and then C, E6. So here we listed all the associations of an edge with certain vertices. Then what happens where graphs might differ from binary relations might be that we might have some multiple edges. I'll just draw them artificially and erase. For example, there might be another E7, another edge, then we would say here what? Oh, that's not in the listing. But in that case, we would say also CE7E across that. This is just not in the listing. In that case, we have that, we'll say that we have multiple edges, and if that doesn't happen, then we say that the graph is simple. So graph simple means no multiple edges. What else there? Yes, and then what? There's also term loop, and that's what the edge connecting a vertex to itself. For example, A, B, C, now here is the graph, but around A we have a loop, so we have edge connecting A to itself. So these are sometimes interesting for combination. In the definition 7.1.2, we talk about different type of graphs. Those are directed graphs. Definition 7.1.2. So directed graph is G equals BE, but in E we have directed edges. What does it mean? It means that the vertices are connected in one of the directions or both, but not, let me see what I have here, just 1, 2, 3, 4. keep it the same as in the notes, 1, 2, 3 here, and 4 here. And then we have like connector now at the arrow that says edge goes from 2 to, and then we have 1 goes to 2. So they are connected both ways, but we have to specify that, let's say 3 is connected to 2 only one way. So if we have this to be E1, this to be E2, and then 1 and 4 are connected this way, and 2 and 4. So for example, we would say what? 1 E2, 2 from 1 to 2, but also on E1, 2 E1, 1 from 2 to 1, and so on. So, but we'll rarely mention directed graphs. In our course, we'll mostly be concerned with just general graphs. And then example 7.1.2. So example, just showing you how important graphs are in everyday life, in computer science, for all kinds of recording properly some information. For example, here it says what? We represent the airports that an airline serves as a vertices. For each daily flight from CTU to CTV, we can associate an edge UV. So here's, let's say, New York, then San Diego, let's say San Francisco, and then we would have edge connecting New York to San Francisco for one flight, for the other, for thirds. Usually graph should be okay. Usually if there is a flight between two towns one way, I think they always have the other one. But if you want specific flights, specific times, then this would be like a multi-graph, like here for example, then here, and then multiple edges for different ways for different flights that exist between towns. For example, that's one example of a multi-graph. Then, so as I said, we are just introducing the main terminology here. For in example 7.1.3, I want to specify some graphs that are quite often used. One of them is complete graph. And then K33 also next to it. What is the difference? K5, when we say K5, we mean there are 5 vertices, and then everybody is connected with everybody, like pentagon, all the possible vertices. But it's simple, so no vertex is connected with itself. And then K33 has like this, 3 objects on one type, like black points, and 3 blue points. So there's partition of 3, 3, and then everybody is connected, from one partition is connected with everybody from the other. So star is connected with all 3 dots, second star the same, third star the same. So we are saying, and then of course that could be done then 2, 5, so all kinds of partitions. These 2 are quite well known for some examples. Then there's a notion of a subgraph. So what is it? So as I see, there are tons of definitions here. I can phrase this. So let's say that this is graph G, and then we want G prime equals what? D prime, E prime, and we have G is D, E. So we'll say that the G prime is subgraph, so that is like less equal. If what? If set of vertices is subset of vertices and set of edges is subset of set of edges. So generally, what, for example, what did I do there? I just took these 4. No, I took all of them actually. Here are the stars. And then just, so a set of vertices is the same, but then we left just a few connections. Here they are. So no new connections are allowed, and then some connections you cut off, some of them you keep. So here is your G prime, and G prime is a subgraph of G. All right, so this is some first terminology. Section part 711 is about degree. Degree of a graph. So here's definition. Let the G be a graph and the U a vertex of G. Degree of U is the number of edges associated with, or sometimes with edges in G, incident with the U. So just number of those edges coming out or getting into the vertex. And here's the theorem. If G is a graph with n vertices, V1, V2 up to Vn, with corresponding degrees D1 and D2, no, I don't call it, okay, Dn, and S is the number of edges. Then D1 plus D2 plus Dn is 2S. In the lecture notes, I give a proof by induction, and it's really nice and clean proof. Here, I'll just, as alternative, I'll give you just common sense proof. What would that be? Because what? If we have, although I told you many times, example is never a proof, but here is the idea. The idea is, when you have all the edges, they must connect somewhere. So for each of the edges must be counted somewhere. So if there is an edge, it must be counted among certain vertices. So these are V1. V1, V2, V3, V4, V5 with the degrees. And then what? If this edge connects V2 and V5, then that one counts what? Counts in D2 and it counts in D5. So each of them, each of those S edges must be somewhere there. But why 2 S's? Because each of them was counted twice, because this edge was counted for V2 and counted for V5. That's why it's equal to 2S. As I said, you can see in the notes, just proof by induction. It's also elegant because when we increase the number of edges, then how do we go to the induction hypothesis? We just cut off one edge using that hypothesis and then increase 2 of the degrees by 1. So it's a good exercise in induction, so you can also try that. Of course, if it doesn't make sense, let me know. All right, here's a nice exercise. So what we are trying here is to have with these simple results to actually be able to make some conclusions about the graphs. So corollary is kind of a consequence of a theorem. 712, every graph has even number of odd degree vertices. And why is that? It's very simple proof. We'll let the labeling be like here, so vertices V1, V2. But let me first list the odd ones. So V1, V2 up to VL are odd ones. And then VL plus 1 all the way to Vn minus L are even ones. But that's not, it's not special, I just make a label so that odd ones are labeled first. Then using this theorem, we know for their appropriate degree that D1 plus D2 plus DL plus DL plus 1 plus Dn minus L equals 2s. And then very nice, elegant move. We just reduce modulo 2, even odd. So if I do modulo 2, obviously this is congruent modulo 2 with 0, even number has modulo 2. The remainder 0. So look at these guys, look at these guys. These guys are odd ones. So modulo 2, each of them gives us 1. So it's 1 plus 1 plus 1 L times. What about these? These are even, so they give modulo 2 remainder 0 and minus L times. So altogether, 1 plus 1 L times is just L, 0 is not count, L is congruent with 0 modulo 2, which means L is even. And L stands for number of odd degree vertices. So very simple, elegant proof, could be nice problem for the final, because it really needs minimal technology, but needs some skills improving. And then now I'd like to analyze one type of graphs associated with polyhedra for two reasons: to practice a little bit in this introductory section, and also to show you how we can make some nice, powerful conclusions, especially about some geometric objects. So first, next example is actually quite detailed. 715. This is about polyhedra. What are polyhedra? Are geometric solids that are closed, bounded, and whose all the faces are flat. So generally, it could be something like this. Let me draw one of them. Something like this. And then one pyramid on the bottom. This is a polyhedra, for example. This is octahedron. So what can we say about this polyhedron? We are interested here in number of vertices, number of edges, and number of faces. So for example, this one has how many vertices? 1, 2, 3, 4, and top and down, that's 6. What about edges? 4 on the ground, 4 above, 4 below, so that's 12. How many faces do we have? 4 above the ground, 1, 2, 3, 4, 4 below, so that's 8. And what's interesting, when you add up faces and vertices, which is 8 plus 6, we get number of edges plus 2. So that's a famous Euler's formula that's true for polyhedra, and that one says what? That the vertices plus faces equals edges plus 2. And we want to play a little bit with this formula from geometry, and then later on we'll connect it with graphs and see why would that be interesting for us when studying graphs. But for example, when you have analysis of this type, we can make some interesting conclusions. For example, we want to describe all the regular polyhedra. What are the regular polyhedra? Those that have regular polygons as their faces. For example, this one has triangles. They might be squares, like for the cube. They might be pentagon, or whatever they might be. So here's an interesting way how we can describe all the regular polyhedra using this formula. This is all beautiful result. Let me introduce a little notation here. So you see, at every vertex we have certain number of edges meeting at that point. So these are the edges, and that one we will call M. So this is M is the number of edges meeting at the vertex. So M, number of edges meeting at a vertex. And N will be just number of sides of each face. Okay. So if we take that, maybe this should have done to be red, and that's how I label it red. So for example, here I just have 3 edges on each face, so N would be 3 in this example. So we can say the following. All right, so each face needs to provide an edges, number of sides or edges. So generally, number of faces, each of them gives me n edges, and that would give me the total number of edges, but I have to divide by 2. Why? Because this way every edge is counted twice, because 2 faces share the same edge. So because of the double count, I have this formula. Also, what can I say here? Each edge, so what else? Every face has also, every vertex, so every face has n vertices, because number of vertices in the polygon is the same. So that would give me the total number of vertices, number of each sides or vertices of each face. Then if I go face by face and count n vertices here, n vertices here, n vertices here, I have f times n vertices, but then they are appearing m times because each vertex is, this vertex is shared by 4 different faces, so I have to divide here by m to get a number of vertices. So but then we can replace this in the equation and get some interesting analysis. So what do we get? A v, which is fn over m, plus f equals fn over 2 plus 2. Then we get all the f's on the same side, so I get n over m minus n over 2 and plus 1 equals to 2. New common denominator, so we get what? 2 m's. So we get what? 2n minus mn and plus 2m equals to 2. And now what? Since this f is positive number and 2 is positive number, we know that 2n plus 2m minus mn must be greater than 0. So what is that telling us? If we get mn on the other side divided by 2, we get m plus n to be greater than mn over 2. They're all positive numbers. From here, there's a nice conclusion that what? Either m greater than or equal to 4 or n greater than or equal to 4. Why? No, sorry. Either n is less than 4 or n is less than 4. Why? If we argue by contradiction, assume the opposite. that m is greater or equal 4, n is greater or equal 4, then what? Mn over 2, since m is greater or equal than 2n, and mn over 2 is greater or equal for 2m, because this n is greater than or equal 4, then I would get that mn over 2 would be greater than or equal. If it's greater than both, it's greater or equal than their average, which is m plus n. But that's contradiction, because we saw that mn over 2 is strictly less than m plus n. So this contradiction says they cannot be both greater or equal 4, so one of them must be 3, because less than 3 you cannot have polygon with less than 3 sides. So either you have triangles when n is 3, or you just have n equals 3, which means just 3 edges are meeting at every point. And then I don't know which one we analyze both. I did n equals 3, so case 1. Says n equals 3. So what is that telling us? Well, we have the following. We have what? F times, if n equals 3, we'll get what? 6 minus 3m and plus 2m over 2m equals to 2. So we'll get what? F times 6 minus m over 2m equals to 2. So what is that telling us? It's telling us first that m must be less than 6. Because if I want this to be positive, so m must be less than 6. So what are the possible values? And we know that n is greater or equal 3. So we have the 3 cases. First one, m equals 3. And then second one is m equals 4. And m equals 5. So these are the only possible polyhedra in the case 1. When m equals 3, what is that? That's a pyramid. So three triangles and 3 of them meeting. If m equals 4, that means triangles, but there are 4 of them meeting. That's exactly our octahedron. And then if m equals 5, then what happens? So if m equals 5, then we'll have the following: f times 1 over 10 equals to 2, so f equals 20. So if f equals 20, that means that we have 20 faces, and that shape is called icosahedron, because icos is 20 in Greek, icosahedron. And those are, I'm not going to draw it because it's quite elaborate drawing, but anyway, here are the possible cases if we have only triangles on the side. If we have, so the other case, let me try to squeeze it in here, case 2, if we have that m equals 3, only 3 of them meeting, then in the same way we will get either n equals 3, n equals 4, or n equals 5. n equals 3 is still pyramid. n equals 4 is a cube, because it has squares, 3 of them meeting, and n equals 5, I'm not going to draw again, this one is called dodecahedron. Oh, what do you mean with spelling? With C, dodecahedron. So there are actually, but this one is repeated, so there are basically 5 classical regular polyhedra. One is pyramid, or tetrahedron, so-called, octahedron, cube, and then those 2 exotic, one icosahedron and dodecahedron. All right, and that's an interesting analysis from the Euler's formula. How does that match with our analysis of graphs? Generally, let me erase this actually. I want to have a little story about dodecahedron. So dodecahedron, dodecahedron. What did we have there? It has pentagons, n equals 5, 3 of them are meeting, and then if you calculate number of faces according to that formula, we'll get 12 faces. And then let me draw a picture. So I just copied the picture from the notes, takes a little longer. Takes a while. Okay, and then inside the net, and then each of them is connected with 5 of them. This one here, this one here, this one here. So what's this? It's a little complicated shape, but actually what happened is we took one side, so this is how it looks. So at each point we have 3 faces meeting, and then each of them is a pentagon. A little better picture is in my notes. But generally what's interesting here is the following. The way we obtained this shape is that we just stretched one side, one of these pentagons, so that the others can project inside that one. And then what we got here, we got a planar graph. So this is the graph. So vertices of pentagon are now vertices of the graph. So here they are. How many vertices do we have, by the way? The number of vertices is what? We have 12 faces. Each of them has 5 vertices, but each vertex is shared 3 times, so it would be 20 vertices. And then faces is 12. And then the number of edges is 20 plus 12, so it's 34. Is that correct calculation? So we have what? Calculate something around it. So there are 12 faces, each of them has a pentagon, 60 over 3 is 20. And there are 12 faces, so it's 20 and 32. What about number of edges? It should be five round, and one, yeah. So this is 12. So what? Let me correct this. So number of vertices, 12 faces, 5 each, 3 divisions. So that's 20. Number of faces is 12. Oh, sorry, number of edges, when I add it up and subtract, number of edges should be 30, which is normal because why? We have what, 12 faces. Each of them has 5. When you divide by 2, that should be 30, and that matches. But what is interesting here, generally, if you look at this graph, then this graph is drawn in the plane. Those are called planar graphs. So tell me what? The faces that were in space now became regions. So here's region 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this is 12th region is outside. Actually, what's below that we projected onto. And then, so here are the, so this graph is planar. That means we can draw it without the edges intersecting each other. And there is a theorem that actually says that that's exactly the property of planar graphs, is actually exactly what we had a minute ago, and that is that number of vertices plus number of faces is number of edges plus 2. So all the planar graphs must satisfy this, and the other way around, if the graph satisfies this with certain other restrictions, then it would be planar. So for example, how we can use that, if you remember K5, which is all 5 connected, did I miss something? Yeah, this one. So the question is, can I redraw this more carefully and avoid hitting each other? So can this graph be redrawn so that no edge intersects one another? And the answer is no, why not? Because look at this in K5, we have what? Number of vertices is 5. Number of edges is basically for every couple there is edge connecting them, so it's 5 choose 2, which is 10. So if it's planar, it must satisfy Euler's formula. So then we have what? F equals E plus 2 minus V, which would be 7. But then what? If we have that, then we would need much more edges, because 7 faces would need the enormous number of edges. So number of edges should be what? Greater or equal, each face needs at least 3, and then there is that sharing, but that's 10.5, and that's bigger than 10. So contradiction, so you cannot have that. So remember, each face, so I would need 7 faces according to Euler's formula, but 7 faces, each of them requires at least 3, at least triangle, that's the smallest polygon. Then we would need 3 edges with the sharing twice. We would get 10.5, but we have only 10, so that's why K5 cannot be drawn in a plane. What about K33? That's a little more subtle. So if I have 3 points and 3 stars, and I remember once spending a great amount of time trying to see if that's possible or not. So to see if I can draw the road so that they don't hit each other. So for example, this one connects here, then this one connects here, this one connects here, so that looks good. Everybody's connecting with the top one. And then what? Then the second one avoids it. Goes like this. And then this one goes around, connects. This one connects here. It looks promising. But then when the third one comes, you must hit one of them. Why is that? It's the same reason. K33. Number of vertices is 6. Number of edges is 9, I think, because each star is connecting with 3 dots, and then 3 times 3 is 9. So what's number of faces then? Is 5. Why? Because edges plus 2 is 11 minus 6. So V plus F is E plus 2. So V6 plus F is 11, so F is 5. Now if we try this trick from a minute ago, 5 times 3 over 2, because each of them needs triangle, does not exceed 9. So we cannot reach contradiction as a minute ago, but here's a trick. This one, this graph can never have triangle. Why? Because if you have a triangle, that's a neat little thinking. So if you have a triangle like this, then two of them must be of the same type. Either two of them are stars or two of them are dots, but that's prohibited. So if I have two stars, then stars are connected, but that's against the rules. So this guy actually has no triangles because of the definition. So every face, each face, has at least 4 edges. And now we have what? 5 times 4 over 2 edges at least I need, which is 10, but I have only 9, and here's the contradiction. So generally, because of Euler's formula, there is no way to draw this in a plane without intersecting. So let me put this into perspective. First half of the section is necessary for our future communication in this chapter. This second part of about Euler's graph will be less important like quizzes, exams, but it's an interesting result and good illustration of why is this interesting to study.